Now let me take you one step further. Having this idea and having this proof in front of us, there is something more that we can say. So what we can say is, well, remember what I did with product rule? I took the product rule, I wrote down the proof for you, and then what? The purpose was not to verify that the product rule works, right? What was the purpose? The purpose was to discover the reason why. The main idea why it works. Distributivity happened to be the main idea. Now let's do the same here for this step. What is it that makes this work? That makes that expression constant? Well, differentiation is technical stuff, right? We know how to differentiate. Then the area of this parallelogram is 0, regardless of conditions there. So the only important step here is this conclusion that what? That the two vectors, position and acceleration, are proportional. So let me emphasize that. Position is always proportional or parallel to the acceleration. So that's the minimal thing that is needed, right? We only need that to conclude that it is 0, and therefore to conclude that Kepler's law holds. But now, as we figured out the minimal condition needed, well, let's just look at possibilities. When is it that this condition is satisfied? Is it only gravity that makes this happen? You have two bodies flying, and all we need about that situation is that the force acting on one of them is toward the other. Doesn't it happen in electricity? When you have one charge maybe positive and another one maybe negative flying out there, don't you have electrostatic force bringing one to the other? Don't we have these two vectors proportional then in that case? Well, but if yes, then Kepler's law holds. Have you heard of Kepler's law in electricity in that context? What about one of the charges being positive? The force is in the opposite direction, but is it still proportional to the position? Yes, it is. So Kepler's law holds in that case. So that means that if you have two charges flying out there, and at this time you don't even know what the trajectory is. Nobody told you, and I'm not telling you what it is, because I don't know. So this charge flies following some trajectory. What we can conclude now, what we just proved, is that as this charge follows this track, and we look at this radius vector, the area swept by that radius vector is proportional to the time spent. Without knowing much about it. Now, what about one step further? There is possibility of more than just electrostatic interaction. That can be a massive object, right? that can be a massive object. And in addition to the electrostatic interaction, they may have gravity interaction. And that gravity adds some force, gravity force. So the resulting force acting on this particle is the sum of electrostatic force and the gravity force. They're looking in the opposite directions, but the sum is still proportional to the same thing, right? Even in that case, Kepler's law holds. And so I will leave you with that. So whatever you do, you may now look for possible applications of Kepler's law. And you can claim that is your law. Kepler never claimed that. Nobody knows whose law that is. Just discover it and claim it's yours.